So last class we started looking at the architecture of a receiver. So we said you are trying to resolve a receive signal which is very small in the presence of very large interferers. And these interferers could be from your own transmitters, other transmitters and so on. So you are going to try to resolve all the channels of all the users at the same time, and then try to choose the particular channel you want afterwards later, maybe in the baseband, in the analog baseband or the digital baseband, right? That also makes things easier for you because you don't need this kind of tunable selectivity at RF. Is that clear? And we said, we started off with looking at the RX system. So we said from the antenna you will first need an LNA. Okay? What does a low noise amplifier do? It adds very little noise while amplifying the signal. As simple as that. Right? You need to add an ideal amplifier would amplify it without adding any noise. So the signal to noise ratio at the input will be the same as the signal to noise ratio at the output. Okay? It will amplify the input noise as well as the input signal naturally. Okay? After this, what do you have? Yes. Okay, you have the mixer, but before this, you also have the band select filter, which I didn't show today. So let me show that to have the same. So after the LNA, you have the mixer, right? What did we say the mixer does? The mixer performs frequency translation. We have a signal which is being transmitted on top of a carrier, right? And then when you receive it, you demodulate it back down to baseband or intermediate frequency or whatever to any other frequency using a mixer. So therefore the mixer requires a second input. So let us say this was FRF. The mixer will require a second input which will be FLO. Okay? And the output frequency is some FIS. I'll call IF the intermediate frequency. Okay? You can choose this intermediate frequency to be anything you want by choosing FLO. Right? So one of the things we are going to look at today is how do you choose this intermediate frequency. After this, what would you choose to do? So you have brought your signal down, you have amplified it a little bit. Okay, you have brought it down in frequency, then what else? Maybe some more amplification is in order. Why not do all of it up front before the mixer? Huh? Stability issues. What kind of stability issues can you imagine here? Okay. So what could be the problem? When do you have a stability problem in a system? If you have high gain, when do you have stability problems? Huh? What? Okay. That is a definitely valid point. Designing an amplifier at higher frequency is almost always tougher than designing it at lower frequencies, right? You want a 10 megahertz amplifier versus a 10 gigahertz amplifier. The 10 megahertz amplifier is probably going to use lesser current. It is less sensitive to parasitics, right? And you may not have to use inductors. There are so many advantages. Okay, but now coming back to your point about stability. So why would there be a stability problem? Let's say I have a very high gain amplifier. When would there be a stability problem? So you mentioned something called phase margin. What is that? No, what is phase margin? What you said is, stability you defined it in terms of phase margin. You should be able to define phase margin independently. Right? So what is that? Added to what? So what happens if you add more phase lag? Let us say I had an amplifier, okay, gain was exactly 1. Let's say my LNA I am choosing such that A was 1, gain is 1 and phase is minus 180 degrees. What will happen? Will it start oscillating? Why not? You need to have feedback, right? If you, what the, all the phase margin criteria tells you is, if you take the system and apply feedback across it, then it tells you something about the stability of the system. Okay, that is a valid point. If you are saying that the parasitics could actually, you could have a parasitic feedback path, definitely that is valid. Now, do you think that will be, how important do you think the parasitics will be? With respect to frequency or with respect to something else? Okay, with respect to frequency. Anything else? Could they depend on anything else? Okay, at least okay. So, we'll come to that. But primarily in terms of parasitics, what kind of parasitics are you thinking of? What kind of parasitics lead to this feedback problem? Some input to output capacitance. Okay, what does the input output capacitance depend on for a normal amplifier? The sizes of the devices. So let's take a very simple common source tuned amplifier. So let us say this is V in, this is V out. So I may have some parasitic gate drain capacitance on this transistor, which is giving you a parasitic feedback path which could degrade your phase margin. Correct. If you actually take this loop, analyze this as a loop, the phase margin will depend on the value of this capacitance, right? Okay, so when will this capacitance be large? When the devices are large. Okay, normally if you take an LNA, a low noise amplifier, you don't have to worry about this, because the device sizes will be pretty small. The cases where you have to worry about it may be in a power amplifier. It's still ideally an open loop system, but because the devices may be several millimeters large, okay, you will have a parasitic CGD, which could lead to stability problems. Normally in an LNA, it shouldn't be a problem. You will still need to check, but it shouldn't be a problem for a well-designed LNA. Okay. Now you said something about linearity. So he said something about linearity. Okay. So let us look at what he means by. Okay. Now, what do you understand by linearity or non-linearity? That is what you understand by non-linearity. If I tell you an amplifier is non-linear, is that what you would understand by non-linearity? So I have Vi, I have Vo. Okay. So if I tell you this amplifier is non-linear, what is the easiest way of explaining it? Putting in one frequency and getting multiple frequencies out is an after effect. It's an effect of the nonlinearity. That is not the way you would define nonlinearity. Exactly. So the input output transfer function, if I plot Vo versus Vi, okay, maybe let us assume this differential, okay, I may get something like this. Maybe this is a case of a system with soft nonlinearity, right? It is well behaved. I can give you a case of an example of a system. Something like this is highly nonlinear. This case is a soft nonlinearity where it is very linear for small signals. It looks very linear for small signals. As the signal keeps getting larger and larger, it seems like it is saturating in some form. Okay. So what happens if you actually put in a lot of gain up front here in the LNA? What will happen is the signal will saturate, so the mixer needs to be able to support even larger amplitudes, input amplitudes. Okay, that could be a problem. Okay, we are going to look at this systematically in the next few classes, but that could be a problem. You don't want to put too much gain up front. If you don't put enough gain, the signal may be too small, so the noise of the mixer itself may swamp out the signal itself. So there is a certain amount of gain you need to get up front, and a certain amount of gain you need to put at the back end. Is that clear? Okay. What else do you need after this? maybe some more filtering. We will discuss what that filtering could be. Okay, I'm going to put it like this, some amount of filtering, and maybe this goes into some demod circuitry, and the output of this will be the baseband. Okay, this is a very, very simple receiver system. Okay, so this system is called the actually it's called the single conversion super heterodyne system. Okay, this is called a single conversion super heterodyne system. Okay. Okay, so let us try to analyze this system to see what happens to the signal at different points. Okay. Okay, so let us say, actually analysis of the band select filter should be very straightforward. All it does is remove the frequencies you don't want. LNA is just an amplifier. The primary thing which needs to be discussed is this guy. Is this guy. Is the mixer. Because we still don't know what a mixer does. All of you already know what an amplifier does, right? And even a low noise amplifier, you know what noise is. You are saying you want to amplify with very little noise being added. Even that seems very straightforward. Let us look at what a mixer does first. Okay. So what does a mixer do? There is a specific reason why I have drawn it with a circle with an X inside it. What do you think it represents? It's a multiplier. Okay. So all you are doing is, let us say this was FRF, FLO, FIF. Okay. So let us say the RF signal was some A cos omega RFT times B cos omega LOT. Okay, let us say the mixer is going to multiply these two signals. What does this give you? You can resolve the signs, the multiplication of the cosines, you can resolve it into sum of two cosines. Okay, this will give you AB by 2 times cos of omega LO minus omega RF plus times T plus cos of omega LO plus omega RF times T. Is that okay? Looks okay? So let us say I originally had my signals like this. Okay, these are my two signals at the input. Okay, so what I am doing is I am multiplying it with this in the time domain. So in the frequency domain, what am I doing? I am doing a simple convolution. Okay. So okay. So I am convolving it with a cosine. Right? What will I get? Yes. Correct. Yeah, this should also be the thing, but I am just taking in reality you can think of any signal as a sum of cosines. Okay, so it shouldn't matter. Okay, I'm going to convolve it. What will I get if I convolve it? Shifted to the right by, what will get shifted to the right? Spectrum around omega RF will get shifted to the right by, to the left by omega LO. Okay, so is it easy to draw it? So let us say I go ahead and draw this. So what he's telling me is it will look like this. Okay, so I'll get this, something like this. So this will be omega LO minus omega RF minus of that. Okay, minus of. Does it look okay? I'll get this. Okay, because that you already know, right? You are supposed to get two components. One will be related to omega LO minus omega RF. The other will be related to omega LO plus omega RF. So the whole thing will get shifted. Now the way I have drawn it, what does it assume? It assumes LO is greater than RF. Okay, that is the assumption. What happens if LO is less than RF? Yeah. So if LO was less than RF, these two guys will just get shifted. So you will get something like an inversion in the frequency domain for the signal. So right now I have shown symmetric signals. If I had actually shown the signal something like this, one-sided, okay. So your okay. So let us say the signal look like this. I am looking at a one-sided signal, and I am looking at the case when omega LO is less than omega RF. What will happen? The original signal look like this, but on this side I'll get something like this. I'll get an inversion, right? What will happen to the signals here? The ones on the outside will not change. Okay, so the ones on the outside, they will look exactly the same. Sorry, something like this. Okay, is that clear? Okay, so this is very straightforward. Now what do you need to do? Now you have done the mixing. What is this frequency called? Omega LO minus omega RF. This is your intermediate frequency IF, right? So that is the one you want to amplify and process. So what do you think the IF filter should look like? IF filter will be a low pass, maybe looking like this, maybe something like this. This is your IF filter, right? So because you know you're not interested in omega LO plus omega RF terms, you want to filter them out anyways. Okay, those are the sum terms. Now I have not shown this here, but the amplitude will be half. Okay, it will be AB by 2. It won't be half. It will be AB by 2 in this case of ideal mixing. Okay. So we can look at two cases. Somebody said, your IF amplifier is easier than RF amplifier, right? Therefore you want to go to an IF frequency instead of RF frequency. So if you want easy IF design, what do you think omega IF should be? Large or small? Should be very small, right? For easy IF design. Small omega IF. Okay, so you can do both. You can get both high gain as well as you can realize both of these. You can realize high gain as well as high Q filtering. Okay, so this looks fine, right? You choose an as low an omega IF as possible and do everything else and you are done. But as it so happens, there is one more problem. Okay, the problem is, so far we have been assuming that the input is either a sinusoid or a sum of sinusoids which is band limited, okay, to this. Right? You have a very narrow band signal around omega RF, so you can practically consider it, for analysis purposes the same as a sinusoid, sum of sinusoids, and you're done. Right? That seems very straightforward. Now, the problem is the input coming into your mixer may not be just a narrow band, because up ahead at the input you only have a band select filter. You don't have any other set of filtering. Okay, so whatever is there at the input will come in. Okay. Now, suppose let's say this is omega LO and this is omega RF. We'll take the easier case where omega LO is larger than omega RF, and I'm convolving it with omega LO. And what was I getting? I'll just show the positive side, okay, that makes it easier for me. So I'm going to show you the omega IF. Okay, so maybe I'll get omega RF plus omega LO. Okay, this may even be much smaller if I have enough filtering and so on. You don't have to worry about that. Now, suppose I had a signal here, okay, and I'm going to call this omega IM for the image. Okay, this frequency is called the image frequency. So if I consider a signal at if you had a signal at a frequency omega IM, which was omega LO plus omega IF. Okay, so remember, originally you designed omega LO minus omega RF to be omega IF. Okay, now what I am saying is these two frequencies are also off by omega IF. Is that okay? What happens if I convolve that signal with omega LO? What will I get? I'll get a component. So you will get cosine of omega minus omega IF, okay, from this guy. So for the image, I'm going to call it C cos omega IM T times B cos omega LO T. Okay, this will give me BC by 2 I'll get something like this, right? So what that means is this is the same as omega IF, right? So what that means is I'm going to get the image signal right on top of your desired signal, right? And I'll get a second component somewhere up here. So this will be omega IM plus omega LO, which will be exactly 2 IF away from the original component. It will be 2IF away from this guy. Okay? How do you get rid of this problem? This is obviously a problem because you don't even know what is there at the image frequency. Right? Do you know what is there at the image frequency? You don't. So how do you solve this problem? Okay, so that is one option. One option is remove or filter out omega IM component. Where do you filter it out? Before mixing, right? Just before the mixer. Correct? So you want to filter it out just before the mixer. Okay? That seems straightforward enough. So what that means is you actually need let me just add that block here. I'm going to call it the image reject filter. I need it just before the mixer. Okay. So now this image reject filter obviously is rejecting something which is it's operating at what frequency? At the RF frequency. Okay? At or around the RF frequency. It's trying to cancel out the image frequency. Okay? Now, as far as this filter is concerned, which is better, having a low IF or a large RF, large IF? Large IF. Why is that? As simple as that. Okay? What you're going to do is, when you say image reject filter, what you're talking about is something like this, let us say. Right? The smaller IF is, the closer the image will be to your RF frequency, the tougher it will be to design this filter because the filter needs to be very high Q. Right? So if you choose a small enough IF, you may not even be able to filter out the image. Okay? So from the point of view of the image, so the image reject filter will desire the IF to be very large. Okay? And now these are two conflicting requirements. If you choose IF to be too large, then your IF amplifier and IF filter become much more difficult. If you choose the IF to be very small, then your image rejection becomes a problem. Okay? Now, this is a fundamental problem with receivers. Okay, this is a very fundamental problem, and there are several ways of targeting this. Okay, apart from choosing the IF frequency judiciously, there are several different ways to target this depending on your system level trade-offs. Okay, for example, what I have not talked about here is digitization of the signal. Okay, I have not even put an ADC in the receive path. Any modern transceiver will have an ADC somewhere in the receive path. Question is, where do you put it? If you have the best case of course would be to put an ADC right here. You just digitize the RF signal completely. Okay? Are there any problems with that? Okay, difficult to design on high speed ADC. Anything else? Dynamic range of the ADC. Okay. Anything else? Noise. Okay. Anything else? Matching could be a problem. Okay. What kinds of ADCs do you know? Flash ADCs. Then what else? Delta Sigma, SAR, pipeline. Each of these things has different trade-offs depending on the resolution you want and the frequency at which you can operate it. Okay. Many of them will not even be applicable here. There will be fundamental trade-offs between power, number of bits and so on. Okay. For example, if you want to use a Delta Sigma, is it possible to use a Delta Sigma ADC here? you need to, delta sigma ADC fundamentally requires oversampling. If you're at RF, then you really need to oversample it at a very high frequency. Okay, yeah, I'm coming to that. So because the signal bandwidth is very small, however, you don't need to oversample it. There are, what is this? Bandpass ADCs. Yes, there are actually very different things. Obviously, I think many of you have not done the ADCs course. It is probably not, it's too soon to talk about any of these things here. Okay, there are something called subsampling receivers, right, which take care of, which address this issue. The fact is, even though the carrier is very high, the frequency content is very small. Okay, so in reality, you may not need a, a very, very complex system. You can use a much simpler system to fix this. However, you will find very few people using such kind of receivers in, except for maybe very special cases. Okay, so we will not deal with that here. Okay. So apart from that, you can actually choose, if you suppose you choose a very high IF. Okay, let us say you choose a very high IF. Maybe you don't need an RF ADC, but if let us say IF was a couple of 100 megahertz, you can actually choose digitize the signal right here. You don't need an IF amplifier. You just go ahead and digitize the signal right here, immediately after the mixer, where your signal has been transferred to IF. Let us say IF was a couple of 100 megahertz. If you have a ADC operating at a couple of 100 megahertz, you can digitize it right there. After that, any kind of filtering you need, IF filtering, you can do in the digital domain. You can get very high Q filters. Okay, that is not a problem. Okay, you can do digitization here. Okay, you can do digitization here. You can do digitization at many points. Okay, now a special case of choosing IF. Okay, let us say I choose IF to be 0. What does that mean? So in other words, omega LO equals omega RF. So what is the image? The signal itself is the image. As you keep reducing IF, the image moves closer and closer to the signal until it overlaps. Effectively, the signal is its own image. Okay, so you don't have to worry about the image problem anymore. Right? So your receiver becomes very simple. So let me just draw that here. Do I need an image reject filter now? There is no image, so I don't need an image reject filter. The local oscillator for the mixer will be the omega RF. What do I do? What do I get here? I directly get the baseband signal right here. I have completely removed the carrier. I no longer have an intermediate frequency. So in other words, if at this point, I'm just showing the positive side. I had omega RF, the signal at omega RF. At this point, I'll get a signal directly around baseband. Okay? What do I do next? Next I can just digitize it. Right? I can just digitize it and move on. If I want some more amplification also, I can do it. Okay? But let us say I get and digitize it. I can do any kind of filtering and channel selection, all of that I can do in the digital domain. Can you imagine a problem with this? Huh? Omega RF, why is that a problem? So that could be a problem, right? So what he says is perfectly right. So getting omega LO equal to omega RF could be a problem because this is, let us say, from a remote transmitter. Okay, this is your local reference. You are generating omega LO from a local reference, whereas omega RF is from a remote. How do you synchronize these two? you will need to have a way to recover the phases of the, synchronize the phases of the LO signal and the RF signal in some fashion. Synchronize in terms of frequency, eventually in phase also. Okay? How do you synchronize in frequency? You can use a clock recovery. Where do you recover the clock from? Only at the end of the line you can do it. Okay? Could there be a problem if it is done at the end of the line? So, first of all, obviously if the two frequencies are very far away, it is going to be very difficult even at the end of the line. Okay? But if they are very close, suppose I specify saying, the error in the frequency can only be so many. So, let us say the reference used, if I want to transmit exactly at 2 gigahertz, nobody can ever guarantee transmitting exactly at 2 gigahertz. There will always be an error. Right? What you can specify is the error should be, let us say, 1 part per million. Right? So if you want to do 2 gigahertz, right, the maximum it can be away is maybe 2 kilohertz away, not much more. Or you can say, less than that even. Okay, you can decide how much, what kind of specification you want, and then eventually, like you said, you will have to look at the baseband signal and calibrate out this frequency error. But suppose that is taken care of. Anything else? Suppose you are able to calibrate this out at the system level. So obviously this needs, your processor to get involved to track of what the phase of the signal is and adjust the frequency. Anything else? Okay, if the signal is not symmetric about RF, what happens? Correct. So one problem is, so far we have been looking at symmetric signals, but suppose my signal look like this. Okay? And I am convolving it with okay, what do I get? At the base band, one signal will come like this. Huh? What happens to the second signal? It will be flipped around. I will get something like this. Right? So what happens? How do you separate out these two? Okay. Okay. What is that called? If you only had one side. Okay. SSB mixer. Okay. An SSB mixer is slightly different, but what you are saying is right. So what you want to maybe convolve is only with this, is what you are saying. Okay. What happens with this guy? If you do that, well, you lose half the power in the signal. Right? What else can you do? So what kind of signals have this kind of symmetric asymmetry in their complex signals? So if I have a signal like this, so normally you can have symmetric signals like this, okay, or you can have where let us say, what are you used to? You are used to x of f, right? X of f equals x of minus f. So that is one possibility, and the other possibility is maybe like this. Okay, x of f is not equal to x of minus f. What is this? What kind of signals have this property? X of f equal to x of minus f. If you have x of f equal to x of minus f, this overlap is not a problem. Huh? Huh? Real signals, right? So if you have real signals, yes, of course, I am not even looking, I am just looking, right now I have only said magnitude, but yeah, you are right, that will also be there. Okay, but obviously this is another requirement we taken care of. Okay, can you take care of this in some other way? Oh, okay. That's an obvious. Okay. But suppose that was not possible. Okay. Let's just think about it because I want to cover a couple of other things. So this is an obvious problem, right? You need to find some way to take care of it. Okay. Now, any other problems you can think of with this kind of receiver? Low frequency noise. Remember we talked about flicker noise yesterday, right? So you have a receiver with, let us say, even this ADC, okay, or if you had an amplifier here, or any kind of filter or anything you have here at baseband, okay, what will happen is, I am going to have flicker noise, okay. At low enough frequencies it is going to dominate over, it's going to kill my SNR of the signal. Okay? How do you solve this? Yeah. This sonic flicker noise after the mixer, not before. Before you don't care. Sonic flicker noise after, that's why I said ADC or any amplifier you have after that. Okay? How do you take care of this problem? Do some chopping. I thought a mixer is what chopping is, right? How do you modulate flicker noise at higher frequencies? Okay, what does the chopper do? Okay, so take me through this. Okay, so I have an amplifier. Okay, I want to, I have an input signal here. I want to get A times Vi. This is an amplifier of gain A. Okay. How do you chop this to move flicker noise to higher frequencies? Chop at the input and output. Okay, so I'm going to chop at the input and output. So what frequency are you going to use for chopping? So what you are saying is use an higher frequency effectively. Instead of doing this, I could just choose a low enough IF and do this, right? There's no need to do this. So what else can I do? So this is chopping, but that is probably redundant here. What else can you do? Obviously you can try to reduce flicker noise by using huge devices. That is an option, but naturally you'll be restricting the bandwidth of your system, right? You'll need to burn more power and so on. Anything else? Apart from flicker noise, what other problems can you have? Have you heard of DC offset? You heard of DC offset? Every amplifier, due to mismatch effects, it will have a certain DC offset. The DC offset could be fixed or slowly time varying, right? Slowly time varying DC offset will look like, will have the same effect as flicker noise, because flicker noise is also at low enough frequencies. How do you solve the DC offset problem? Is DC offset a problem here? Naturally. Okay, because then what you will do is you lose some portion of the signal here. It's going to swamp out, because DC offset could be quite high actually, several tens of millivolts. Okay, so what do you do? So one option is calibrate, right? The other option is maybe use no, calibration is cancellation, right? I would assume one option is you measure the DC offset before you receive the signal and then cancel it out, and so you have a DC offset compensated amplifier. You can do it. Flicker noise will still be a problem. Maybe you can use very large devices, burn a lot of power. Of course, a simpler, maybe a more modern solution is to use if you have a broad enough signal, what happens is you choose not to transmit anything at DC, because this will be till a few kilohertz, right? So what happens is you choose just, your signal may be 5 megahertz or 10 megahertz wide. You just, and most modern systems are, use OFDM modulation, where you have a whole bunch of subcarriers, right? Maybe hundreds of subcarriers even. All you do is choose, around DC you don't transmit anything, or you don't care about what you transmit, and you don't have to worry about it. Your information, your data rate will come down by very little, because you have hundreds of carriers. That is another way to do it. Okay, there are many ways to do this. Exactly. So one option is, another option is to just couple it out using a series capacitor. Only thing is the capacitor will need to be huge. Okay, because you are talking, the relative frequencies you are talking about here are, right, very low. the capacitor will need to be really large. That is another way of doing it. Okay? Okay, so actually this architecture, let me go back, is called direct conversion receiver. You're going directly from RF to baseband, also called a homodyne receiver. Okay, so you don't have any image problem. Obviously the receiver is very simple. Your ADC needs to be fast enough only to get the signal bandwidth. It doesn't need to be fast enough to do anything much further. Okay, filtering is very simple, it's at baseband. Most things are simple except for this DC offset and flicker noise problem. If you can take care of those two, this is the simplest receiver. In fact, I'll venture to say that most modern receivers in your mass produced modern receivers are like this, primarily because they are very simple. Okay? And I wanted to do a couple of examples, but I just posted on the class website. I just wanted to do a couple of, one example for AM radio, for choosing the IF and so on. But what I'll do is I'll post the notes on the class website, and you can just go through it, and it's very straightforward, exactly what we've been discussing, except with specific numbers. Okay? Because one thing to remember is that your image frequency, right? Your image frequency may actually be in band quite often. Okay, if you choose your IF to be small enough, your image frequency could just be another signal in the same band, somebody else's received signal. Is that clear? Okay, let's stop here and continue on Friday's class.